Okay. More radio wave characteristics. HF propagation, reliable long distance communications. And when you say reliable, it is heavily dependent upon atmospheric conditions, but once it's on, it's typically on, and you can enjoy some time on the radio. There are certain things that can happen that can make it almost as sporadic E. Amateurs use HF frequencies. HF signals bounce off of the various different layers of the ionosphere, and allows contact around the world. Like I said, I think my farthest is Hungary or Bulgaria. I can't remember. I'd have to look at the distance. And that's with an antenna that's set up that would east-west, so it's typical radiation patterns would be north and south, since my wire runs east to west, because it radiates broadside to the wire. But I'm still managing to reach over into the Eastern Bloc countries. Reliable long-distance communications. Amateurs use HF frequencies. HF signals bounce off the ionosphere and allows contacts around the world. The phenomenon that happens in the ionosphere that reflects the waves is created complements of solar radiation. It creates a high concentration of ions and free electrons, and those ions and free electrons reflect radio waves. From about 50 to 600 miles above the Earth's surface, 3 ionospheric layers, D, E, and F, and remember in the daytime, F separates into 2 layers, right? F1 and F2. D layer being the closest to Earth, F layer being the farthest from the surface of the Earth. And here we have another drawing of what kind of happens, difference between day and night. So you can see it at nighttime. We're limited. We're pretty much reduced down to the F and E layer. But in the daytime, when the ions are getting excited, the F layer separates into 2 different layers, and then the D layer comes awake. What was the drawing on the left here, Bob? Okay. Not on the test, so we won't try to explain it. uh, 6-meter band. 6-meter band is one of those that it doesn't really come around very often, and that's another reason why I haven't built the antenna yet, because I'd have a hard time testing it. But the HF bands are typically better during the daytime when it's warm, because you've got more sun activity that's heating the ionosphere, and that excites the ions, and that's what makes it work. Okay, so when I talked about the gray line a while ago, the line on the Earth, when you look at the drawing, they call it a gray line, and it separates day from light on the Earth in the drawings. Even though it looks very defined in the drawings, it's not very defined when you look at what's going on actually on the Earth, but it's over a wide range. So as the Earth is turning and the light is coming our direction and the Eastern Bloc is starting to get dark, they'll still enjoy those bands until the layers above them begin to cool off. Once the layers above them begin to cool off, then it'll slow down. So to talk to them, I'm generally talking to them midday, and they are beyond, they're starting to get dark. I could probably get them better in the earlier part of the day, but that's when I'm trying to do yard work so that my wife doesn't get irritated with me. That is a difference. There is a big difference. 10 meters is going to become, 10 meters will slow down in the wintertime when it gets cooler. The atmosphere, yeah. Yeah, summertime, what happens is, and my uncle was a science teacher, and he explained this to me, and I still don't understand all of it, but it's not just the fact, like a lot of people think that we're closer to the sun in the summertime, but we're actually not. We're farther from the sun in the summertime. What makes it hotter in the summertime is that the northern hemisphere is pointed more directly at the sun. So when the sun's rays meet us, they're meeting closer to perpendicular, and that's what causes things to heat up. The other things that happen is that the land mass heats faster than the water mass does. So that's how being close to the water regulates your temperature more. But with regards to the radio, the same thing is happening in the ionosphere. The sun's rays are meeting it more perpendicular, so it heats up more and causes more activity in the ions, gets them more excited. Um, 20 meters tends to be the band that a lot of people prefer because there's not a lot of difference between day and night. If it's working, it's working. But 10 meters needs the sunlight. It has to be warm. 40 meters, like you said, gets absorbed by the D layer. So once the D layer comes to life, 40 meters slows down. Now, I've made 40 meter contacts in the middle of the day, but there are not a lot of them, and they're kind of scratchy. So I would have to look at the map, but I mean, so like China is halfway around the world, so that's roughly half. So you're going to be looking at gray line to be able to reach them. So either, let's see, when it's just getting light here or when it's just getting dark here would be the times to try to communicate with them. And I use some spotting web pages that tell when people are on, like if I talk to somebody, I can spot them and say where they're at, and I put their call sign there and let people know, I'm in Florida and I got a great signal from him, so other people can try to contact them. And I've seen people from China pop up on there from time to time, but when I go to that frequency, I don't speak Chinese, so I either hear them and hear that they're speaking Chinese and I can't really communicate with them, or I hear them and can understand what they're saying, but it's scratchy and I can't get back to them. I only have 20 watts available right now. I've got a Chinese radio, a Xiegu G90, but I can't reach China with it very effectively so far. And most of that comes down to the antenna. A better antenna would probably put me out there, and I'm working on building some vertical type antennas. Did that answer your question? Okay. 6 meters, I don't have much experience with 6 meters, but as the frequency goes up, it tends to get shorter distances and tends to get harder to get it to work over a long distance. So, all right, more ionosphere. As you can see there, it shows you basically what's going on with the altitude where the layers, and that's a generalization, of course. D is at 60 kilometers, E is at 100 kilometers, and F from 2 to 300. And remember that the F1 and F2 only exist once the sunlight is hitting it. And then after the sunlight goes away, it goes back to being just one layer. All right. So here's the difference between day and night. F1 and F2 layer, 30 megahertz. If you try to go too far straight up, it's just going to go right straight through. 10 megahertz, you're going to bounce off the well, it says F2 layer. And then you've got the D and the E there below that, lower frequencies. And then you have an example here of a multi-hop. So he's bouncing off the F2 layer back down to the earth, and then back up to bouncing off the E layer, and then back down to earth. So you get that extra hop there, it gives you a little extra distance. But now remember that once that hits the ground again, once it hits earth again, it saps some of the power from it. So it's a weak signal at that point. At nighttime, the F layer combines into one, and you see what happens to that 10 megahertz signal. So that's showing a multiple hop there out to about, 1750 or so, and then another second hop puts us out to around 3500. There are other propagation methods that will bounce across at the top and come back down. And that is ionosphere. Okay. What is this one for, Bob? Yeah. Okay.
Higher up into the F layer, get a longer hop.
Okay. 20. Yeah. Yeah, that's what I was thinking. 21 megahertz about. Okay. All right, so you've got all different signals, and here, rather than putting frequencies on it, we're just going to talk about the bands. The radio UHF signals just pass right through it, not likely to reflect or refract at all. Higher VHF signals might refract a little bit, but not enough to actually make it back to the Earth. Lower VHF signals, and when I say lower VHF signals, we're looking at lower VHF signals, so like 6 meters of 54 megahertz. It's probably not going to reflect back at that. HF signals are going to come back. Lower HF signals are going to come back at some point or another, but it just depends on the distance will depend on which layer they're reflecting off of and your angle of incidence. Which region of the atmosphere can refract or bend HF and VHF radio waves? Charlie, the ionosphere. What is a characteristic of HF communications compared with communications on VHF and higher frequencies? What is a characteristic of HF communication compared with communications on VHF and higher? Okay. Charlie, long distance ionospheric propagation is far more common on HF. HF propagation, sunspot cycle. Long distance propagation on the 6 and 10 meter HF bands best when there are many sunspots. I can't remember off the top of my head now, there's a website that you can go to that tells you what the sun activity is. So you look for heavy sunspot activity, and your 6 and 10 is going to work better. Sunspot increase and decrease over an 11-year cycle. It's called the 11-year solar cycle, and cycle 25 started in 21. It's now 24. And from what I've read, they expect us to peak next year. So next year is going to be a good time for HF, and after next year, it'll start to decrease a little each year. The more sunspots, the more solar radiation reaches the Earth, increasing the amount of ionization in the ionosphere and increasing the ability of the ionosphere to reflect radio waves. So you're getting in at a time when next year or two is going to be pretty good. Skywave propagation. Okay, so this is the same drawing that we had a little bit ago. It shows the difference in angle of incidence and the reach. So on the left there, you see 75-degree angle of incidence for NVIS. Gets you one hop about 100 off of the for about 100 miles, which is off of the F layer. But off of the same layer, if your angle of incidence is 28 degrees, then you're looking at, let's see, what's it say there? 665-mile single hop. Most vertical antennas have an angle of incidence of about 7 degrees. So that's why I'm building vertical antennas. Try to increase my reach with my 20 watts. What's that?
Pointing that way, you got a 7-degree angle, and you point your vertical antenna up, and increase your bounce capability. The radiation pattern is like that.
Yeah. A vertical antenna would be perpendicular to the Earth, and then the radiation signal would be out at approximately, say, yeah, it's a donut around it, but it points out at about 7 degrees above the, not the horizon, but above your point on Earth where it's stationed. It will. Yeah, if you change the angle of the antenna with the ground will affect the donut.
Optimally, it'd be halfway. Go higher than that, you start getting low.
Okay. Let's see. Okay, so this is, we had looked at this earlier at the beginning of this one. And it's all showing the same thing still. Which of the following bands may provide long-distance communications? So out of the ones they have here, and I know we haven't talked about the 23 centimeter band yet, but that's much higher frequency than anything that we have talked about. But which of the following bands may provide long-distance communications? Alpha, 6 and 10 meters. 23 centimeters is, what is that? Is that the 900? 1200? Yeah, 33 would be 900. Okay. 70 centimeters and 1.25 meters. You don't hear people talk much about the 1.25 meters band there, but that's in the 220 megahertz range. So the correct answer is 6 and 10 meters. HF propagation. Ionosphere changes throughout the day. Propagation is best on the higher frequency bands, 10, 15, 20 during the day, and into this 12 and 17 are called WARC bands, W-A-R-C, World Amateur Radio Conference, something like that. Typically no contesting. So if you're not a contest person and you're trying to get on the radio on a day that every band is loaded with contests, 12 or 17 is a good option because the people that don't want to do contests will be there. And if 10 is working, 12 is working too generally. Yeah. Propagation is best on the lower frequency bands, 160, 80, and 40 at night. Irregular fading, the ionosphere is constantly changing. It's not a static thing. It's always changing. Random combining of signals arriving via different paths will cause irregular fading. This is the one that I downloaded when I was taking my technician license off of, downloaded this from the ARRL website. If you Google amateur radio bands, ARRL, this is what it will probably take you to. And it's a good reference, especially in color. The one I downloaded is only black and white, but what is generally the best time for long-distance 10-meter band propagation via the F region? And I don't think we actually said this, but remember we said you have to have daylight. You have to have sunlight in the ionosphere to bring the 10-meter band to life. So what is generally the best time for long-distance 10-meter band propagation via the F region? Alpha, from dawn until shortly after sunset. And the shortly after sunset is how I answered your question concerning how would you talk to somebody that far away. So if things are awake here, they're still enjoying it for a few minutes or maybe even an hour or so after the sun is set, because the ionosphere is still cooling down. From dawn to shortly after sunset during periods of high sunspot activity. What is a likely cause of irregular fading of signals propagated by the ionosphere? Delta, random combining of signals arriving via different paths. This is similar to multipath distortion of VHF and UHF signals, but in this case, the signals are bouncing off the ionosphere, and because the ionosphere is constantly changing, it's very fluid, signals will fade in and out. HF propagation, antenna polarization, not as important on the HF bands as, and we already said this a little bit earlier, jumped ahead a little bit, not as important on the HF bands as the VHF, UHF bands. the signals skip off the ionosphere, and when they do that, they become neither horizontally polarized nor vertically polarized, but elliptically polarized. Horizontally or vertically polarized antennas may be used, and you'll still communicate just fine. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? Which of the following results from either horizontally or vertically polarized antennas may be used for transmission or reception? All right, that is the most correct answer. Yeah, okay. Takeaways. Ionosphere refracts HF and VHF. Fading, random, combining via different paths. Sunspot cycle, long distance on 6 meters. So heavy sunspots, you're going to have better luck on 6 and 10 than if the sunspots are light. 10-meter band, dawn until shortly after sunset. Polarization, ionosphere refracts, and your signal becomes elliptically polarized rather than horizontal or vertically. So you're not important if you're horizontal or vertically polarized, because it's all going to be elliptical once it bounces off the ionosphere. And that is that. And you heard my alarm. That's my alarm to set up, that I set up to tell me that we're 10 minutes away